Okay. So, now the parameter beta is the chirp of the pulse, and since here going back to our sticking to our definition of phi of t, right, neglecting the tiny contribution from the first order term to the carrier frequency, we essentially have phi of t here to be just beta t square. We could very well have a pulse like this. Remember, phi 1 only does a shift in time, it does, therefore, it does not really cause any change in the instantaneous frequency within the pulse. The spectral phase essentially um, is very smoothly behaved in that case, and beta is the chirp parameter, which essentially tells us here that when I take the time derivative d phi by dt, then the beta t square term gives rise to a 2 beta in the frequency, in the instantaneous frequency. Okay. So, here understand that t again can take negative and positive values. So, twice beta subtracts from the carrier frequency on the negative side of the time scale, and it adds on to the carrier frequency, a fixed number for a pulse, okay, on the positive time side. So, the frequency increases linearly with time. Conversely, here of course, we have, when we say the frequency increases linearly with time, it is implicit that we are considering values for beta which are greater than 0. Conversely, nothing prevents us from having beta less than 0, in as much as we can have beta equal to 0, which is the trivial case. Here frequency decreases linearly with time. Okay. So, that sort of a pulse, if I may attempt to make a quick hand sketch of this. The 0 of the time axis is here and 0 of the electric field axis is here. For the case of beta being equal to less than 0, we would well have had I am losing it. Let me give it another try. Doing better this time, I suppose. This would be a beta less than 0. Of course, the horizontal axis is time. In fact, if I recall the first gravitational wave discovered seemed to be negatively chirped. I will probably pull out that paper for the next session or in the discussion. Please go and look at the first LIGO signal. If I recall it right, it was a negatively chirped signal like this in time. Maybe Aditya will check that out for us. Right. So, chirping is everywhere in that sense. So, this is a lot more natural or in nature thing than an unchirped pulse, because dispersion, as we looked at in the previous lecture, dispersion adds an inherent chirp to the pulse very easily. It is just a matter of propagation, and pulses gather dispersion. The impact of dispersion sets itself upon the pulse and it leaves its imprint. The question is how big is the impact of propagation. If the pulse bandwidth is substantially narrow, right, that is to say the amplitude in the spectral domain of the amplitude of the spectrum, we can consider two scenarios, right. We have this, consider two S's of omega, one which is fairly narrow. Okay, I shouldn't make this 0, I should have made this omega naught rather, that would be a better, that would give us a better idea. Whereas, let us take another pulse whose spectrum is substantially broader. Okay, these are two S's of omega. Let us say this is S2 of omega, whereas this is S1 of omega. Okay. So, now the point is, what is beta? Beta is d phi by d omega calculated at omega naught. Okay. This is, you can say, is this beta? Okay, this is phi 2, let us say this is phi 2. It may differ from beta by a factor of 2 based on how we define things, but let us keep that out for a moment. This would be the second derivative. We do not care about phi 1. We could also talk about phi 3, which would have been d3 phi by d omega 3 computed at omega naught. As the pulse propagates, okay, we have, along with the spectral amplitude function, we also have the spectral phase functions of these two pulses. So, let us mark these, say, in green. Phi of omega. Now, the point remains that as this pulse propagates initially, right, d phi phi 2 could well have been 0 when it, say, when the pulse was, maybe a laser spits out this pulse and we did something to make nice nice spectrally flat pulses with a flat spectral phase, okay, which would be called transform limited later, that is what I was coming to say. But then as the pulse propagates, say, in air or through a medium, the amount of impact that the variation of refractive index with frequency has, okay, over the entire bandwidth of the pulse, that is, I can define a bandwidth, a full width at half maximum of the spectral phase function. Okay, I can define this to be a delta omega. The amount of delta phi phase variation that the pulse gathers over this frequency range, where we have an appreciable amplitude, okay, of this spectral intensity function, right. This is evidently, the delta phi is larger for pulse 2 as compared to pulse 1, because the delta omega itself is much smaller for pulse 1. So, in one sense we can say that the impact of the dependence of n on omega, that is dispersion, is stronger for a pulse with a wider spectrum, which, if, as it is in this case, if it is having a flat spectral phase to begin with, in these two cases, pulse 1 and pulse 2 both have a flat spectral phase, the spectral phase does not depend on frequency at all, they would have started as S1 would have been a longer pulse than S2 because of Fourier transform limit. We will talk more about that. But then what happens is, since the spectral content of pulse S1 is narrower, it gets less affected by dispersion, whereas pulse S2 gets more affected by dispersion. We should expect this to happen. One can run a numerical simulation to simulate the propagation of such a pulse, say in glass. Pulses with greater bandwidths, ergo smaller temporal durations, are much more severely affected as compared to pulses with narrower spectral bandwidths and wider temporal durations passing through the same amount of glass, let us say a millimeter of glass. Okay. And I would go so far as to say, we will learn soon, that the impact of dispersion in these cases is to elongate or stretch the pulse. Okay. The impact of dispersion is to stretch the pulse. So, the pulse which started shorter and thinner essentially ends up becoming wider as a consequence of propagation, whereas the pulse which started out much broader would essentially have suffered much less distortion due to dispersion. So, this is a matter of, you can say, propagation affecting pulses of various durations, and in the case that they are well behaved and close to Gaussian, pulses which have different spectral bandwidths. We will get there. Now, a negatively chirped pulse is something different. Now, if we allow beta to be negative, we have already sort of discussed this, then the instantaneous frequency would again be omega naught minus twice beta t, and beta is necessarily negative. So, we indicate that here by writing out beta as minus the absolute value of beta, okay, just to emphasize the negativity in this, and you see the pulse electric field looks sort of the converse of what it was earlier. So, that is a negatively chirped pulse. Now, once again, what are we doing? Let us just recall that all we are examining are the following. We have the spectral phase function phi of omega. Okay, we have expanded it and we have dwelt upon the first three terms, the zeroth order, the first and second order terms in the Taylor expansion of the spectral phase. Okay. In other words, once again, if I may take recourse to a bit of drawing. So, the t axis for us this is omega, this is phi of omega. We have considered the following types of pulses. One where we have just phi of phi 1, phi 2 and the higher order terms being 0. Then we considered second type where this varies linearly, phi 2, 3 and so on becomes 0. And in the third case, what am I plotting? I am plotting the total phi, okay. I am not plotting just the coefficients, the total phi in these cases. Okay, here phi 3 onwards is 0, the other terms are all positive, I mean are all non-zero, not necessarily positive, they could have either sign. I have of course drawn this for the case of positive phi 2, you could have negative phi 2 in which case the parabola would have opened downwards, and For negative values of phi 1, the slope would have been of course negative. So, these are the phase profiles of these pulses, right. In fact, I have drawn each of these phase terms separately, and it would be a sum of these three, the entire phase profile of the pulse. But then the whole point is we have understood to a good extent what group delay does to the pulse, just propagation. It comes about due to a shift in time, which is like propagating in time, whereas phi 2 is the group delay dispersion. Now, let us talk about, since we had looked at chirp and so on, this visual effect is in the time domain. You see, we of course are habituated and, as I like to say, somewhat prejudiced about the time domain over the frequency, although they are both equally good as pulse descriptors. Here we can now start looking at these in the frequency domain as well, because it is in the frequency domain that, as I said, we have any hope to measure these pulses, hopefully unambiguously and completely, right. So, we have a chance or possibility to do that in the frequency domain. Therefore, let us look at the Fourier transform of a chirp pulse. So, this is the expression you see now on the screen is a real amplitude or the real electric field function E of t. This is proportional to, we say proportional to only owing to the fact that, albeit this is an exact expression, a system of units could bring up some constants and whatever. We have E naught, which is a constant in time now. E naught does not depend on time, it is not E of t, first term, multiplied by a real exponential factor, exponent of minus alpha t square. There is no I here, please note that there is no I. So, it is not going to make things oscillate, it is Gaussian. So, minus alpha t square, alpha therefore relates to the first moment of the Gaussian function. Okay. So, it relates to the width of the pulse. So, t square by, earlier we had tau g square, okay, the square of tau g, but this is then the phase term, exponent of I omega t plus beta square plus the complex conjugate. We take this and we now attempt to Fourier transform this. So, how do we Fourier transform this? We essentially club terms with the same powers of t. Here we have exponent of I omega t, but in the preceding term we have alpha minus I beta. So, this is like a standard, if you wish, complex number, exponent of minus alpha minus I beta, and the Fourier transform of this, you know how this is going to work out. This is now a Gaussian function with a complex prefactor to it. The prefactor is not necessarily a real number, it is a complex number. So, this turns out to have a Fourier transform of the following type. So, we leave this as an exercise to the student to work out or look up in the handbook of, say, mathematical functions and integrals, or in other words in a classic text on math physics or engineering math, that the Fourier transform of the alpha minus I beta t square part multiplied by just this omega naught is e to the power I omega naught multiplying the remainder of this, is just going to shift the frequencies by omega naught. The shift theorem plays out inside the Fourier transformed part of this function, which is to say that the Fourier transform of E naught exponent of minus alpha minus I beta squared, this Fourier transform yields E naught exponent of minus a quarter divided by alpha minus I beta omega minus omega naught squared. I mean, there is no omega naught square here, I am sorry. It is just this. So, now, but maybe I should, yeah, let me write it like this. If I indeed had, on account of the kind of expression that I am taking into consideration over here, exponent of I omega naught, I would have had instead of this, or the Fourier transforming process yields us alpha minus I beta. Instead of omega naught, shift everything by, instead of omega square, shift that by the omega naught square variable, right. So, that we have exploited the shift theorem. Okay. So, in arriving at this is where we reconnect to something we did earlier. We neglect this complex conjugate part because it contains no new term, otherwise we would have one more term to this Fourier transform. So, we can now rationalize the real and imaginary parts of this entire quantity, because in the denominator we have a real minus I imaginary part of, or real plus I imaginary part of a complex number, the real part being alpha, imaginary part being minus beta, right. In which case, rationalizing this, we retrieve the fact that a Gaussian function, okay, transforms to a Gaussian. Some Fourier transform trivia remind us of that. That is to say, this piece which is Gaussian in amplitude would Fourier transform to a Gaussian in the spectral amplitude, and then the rest is actually spectral phase. So, we have temporal phase, we have spectral phase, all right. Very well. So, we have Fourier transform this. This is an important entity. Now, does this lead you to thinking about something? I have two Gaussians, a Gaussian in this temporal domain and a Gaussian in the spatial domain. What does, especially a student of physics, would immediately want to yeah, maybe play around with these factors. Okay, I will let this cat out of the bag for a moment. So, what the width of the Gaussian on top, a measure of the width of this Gaussian on top in the temporal domain, okay, delta t is proportional to 1 over the square root of alpha. Now, delta omega is proportional to the square root of alpha square plus beta square divided by alpha by 4. Okay, I am going off screen. So, let me write it differently. Delta omega would be proportional to alpha square plus beta square divided by Aha. So much for my writing. Divided by alpha by 4, right? Let me neat this out. So delta omega is proportional to the numerator twice alpha square plus beta square the square root divided by square root of alpha, that is delta t is proportional to the square root of alpha. Okay. So, does this now make you consider things that you know from physics? We will leave you at that thought and proceed a little bit further and look at now the group delay versus omega for a chirp pulse. We saw essentially something similar in the time domain. So, for a linearly chirped Gaussian pulse, the main takeaway from the previous view graph, which I should possibly have highlighted, is the fact that we now know for this linearly chirped pulse, we have deduced what is phi of omega for the linearly chirped pulse, considering the fact that we know what we define what its phi of t was.